Okay, let's forget the sci-fi movies and the flashy headlines for a minute. Let's get real. What is the actual engineering, the physics, the math? What does it all tell us about our next 80 years in space? We're going to dive into the real-world challenges and the incredible breakthroughs that are just around the corner.
And this quote just nails it. It perfectly sets the stage. In space, there is absolutely no room for error. You can't be close enough. Every single calculation has to be perfect. It is the ultimate high-stakes game. And physics? Well, physics doesn't bend the rules for anyone.
So that brings us to the big question, right? The one everyone asks. When are we really going back to the moon? And when are we finally going to set foot on Mars? We hear these ambitious dates thrown around all the time, but let's cut through all the noise. What does the engineering tell us is the actual timeline?
And really, this is what it all boils down to. On one side, you have the space marketing hype, the big announcements, the amazing CGI videos. And on the other, you have the cold, hard laws of engineering reality, physics, thermodynamics, all the stuff that doesn't care about a press release. In this explainer, we're sticking to the right side of the chart. We're talking about what's real.
All right, first stop, our closest neighbor. Look, the return to the moon is not about planting flags and taking photos this time around. This is different. This is about building an industrial outpost. It's the real start of our space-based economy.
So right now, there's a new space race heating up. You've got two major players, the US and its allies with the Artemis program, and they're aiming for 2027 or 2028. But it's a high-risk, high-reward strategy. It all hinges on being able to refuel a massive starship in orbit, something that has never, ever been done on this scale. Then you have China and its allies. They're taking a more traditional, lower-risk route with proven rocket designs. It's a slower, steadier approach, but it puts them on a very solid path for landing around 2030 or 2031. So why? What is the real prize here? Well, it's this. It's all about the water ice that's been hiding in the permanently shadowed craters of the moon's south pole. Because that water ice is rocket fuel just waiting to be made. Once we can mine it and crack it into hydrogen and oxygen, the moon stops being just a destination. It becomes the gas station for the entire solar system. And things are going to start moving really, really fast. Just look at this timeline. We're talking about a crewed flyby in 2026, then a US landing, followed by a Chinese landing, and right around that same time, the old International Space Station comes down, and the first factory making rocket fuel on another world goes online. The moon is about to become a very busy place.
Now for the next giant leap, Mars. And let me tell you, this is a whole other ballgame. If the moon is a stepping stone, Mars is what you might call a great filter. It's a test that will push our technology and, more importantly, our own biology to the absolute limit.
And it all comes down to this number, 6 to 9 months. Just let that sink in for a second. That's the one-way travel time to get to Mars. And that long, long journey through the most hostile environment imaginable creates two enormous problems that we absolutely have to solve.
So you've got these two massive, show-stopping problems. We call them the two walls of Mars. First is the biological wall. Our bodies just are not designed to be bombarded by deep space cosmic radiation for months on end. It literally shreds our DNA. Then there's the engineering wall. Landing on Mars is a physics nightmare. The atmosphere is too thin to really use parachutes effectively, but it's still thick enough to burn up a heavy spacecraft if you come in too fast. It's the worst of both worlds. So how in the world do you get past these walls? I mean, it seems almost impossible, right? Well, the answer is actually brilliant. And it all comes down to being patient and clever. You see, we don't send the people first. Here's the plan, and it's pretty genius. We send the robots ahead. We send automated cargo ships packed with supplies, construction bots, everything they need. Those robots will do all the dangerous and difficult work years before any human even thinks about leaving Earth. They'll build the habitats, roll out the solar panels, and even make the rocket fuel for the trip home by sucking carbon dioxide out of the Martian air. We're not sending a single person until their new home is basically move-in ready. So pencil it in your calendars. The most realistic engineering-based date for the first human footsteps on Mars is right around 2041. And they won't be camping. They'll arrive at a fully operational, pre-built base ready for them to start their mission. They'll stay for about 500 days. That's how long they have to wait for the planets to align just right for the return journey home. Okay, so once we have a foothold on both the moon and Mars, everything starts to accelerate. The second half of this century is where things get
well, wild. The whole solar system starts to open up. By about 2055, we're finally going to crack one of the biggest problems of living in space, the long-term health effects of zero-G. We'll build these massive, spinning space stations that create their own artificial gravity, just like in the movies. These will be the first places humans can truly live in space for years or even generations. And then, around 2067, something truly profound happens. The first human is born on Mars. Think about that. Growing up in just 38% of Earth's gravity means their bones, their muscles, their heart, their entire physiology will be fundamentally different from ours. So different, in fact, that coming to Earth would be physically dangerous for them. This is the moment. This is when humanity officially splits, and we become a true multiplanetary species. The next game changer is propulsion. Around 2083, fusion engines become a reality. These things are incredible. They provide constant, gentle acceleration, which completely changes the travel time equation. The trip to Mars gets cut from many months down to just a few weeks. A trip to Saturn? A couple of months. Suddenly, the entire solar system feels like it's in our backyard.
And then, just as the century closes out, we take our first real, tangible step toward the stars. Now, we're not going ourselves, not yet, but we'll use these enormous laser arrays on Earth to push tiny little probes on solar sails, accelerating them to an insane 20% of the speed of light. They'll reach the nearest star system, Alpha Centauri, in about 20 years. This is the dawn of our interstellar age.
So, wow. After a century of industrializing the moon, settling Mars, building artificial gravity habitats, and launching our first probes to another star, what does all of this really mean for us? And that leads us to the ultimate question, doesn't it? This journey isn't just about building new technologies or visiting new places. It's about what we become in the process. As we spread out into the solar system, as our bodies literally adapt to living on new worlds with different gravities, will we still be the same humans? Or are we at the very beginning of becoming something entirely new?